Okay, welcome everybody. Today is really a great pleasure to present you our speaker, that is Juan Macias Perez. In fact, I think, I know him since a lot of years ago when he started to do his PhD in Bank, but he was also involved in and collaborate a lot here with us, what will be the CMB group in the ISC. And in fact, he stayed here for a lot of years of time. And in fact, we share the same room, the same office. And I remember that at that time, even the CMB power spectrum, it was not clear even the signal of the first peak. And now you can see how during this year the CMB research have evolved. And we know even, I don't know, the 5, the 5th, the 6th peak, the 7th peak. So it has evolved a lot. And well, after finishing his PhD, he developed his career in Grenoble, where he has now a permanent position. And he has been involved in several projects like archeops, the Planck collaboration, and also now he's involved in NIKA, in the NIKA collaboration. And today he is going to speak about these very interesting new detectors that probably will be very important for CMB, but also for that astrophysical application. So thank you very much.
Okay. First of all, thanks a lot for inviting me here. It was a long time, and it's really a pleasure to come back. So today I'm going to try to speak about the kinetic inductance detectors for cosmology and astrophysics, and actually, in particular, in the case of the NIKA collaboration, for which we have right now 2 cameras. So NIKA is a large collaboration, including people from France, Italy, the UK, mainly, and especially it's led by the Grenoble teams at LPSC, Instituto, IRAM, and IPAG. So we will start for the scientific motivation to having a new camera in the millimeter wavelengths. Obviously, one of the main things is to have a replacement for the current cameras. And I think there are 2 main objectives, or 2 main things that we would like to do in millimeter astronomy. The first of it will be to have high-resolution observations of high redshift objects. So for that, we need a large telescope and very sensitive detectors. And in particular, in the case of clusters of galaxies, via the LZ effect, or Sunday-Solodic effect, and that's the galaxies. The other thing we would like to do is to have very sensitive polarization surveys that can be in one hand on galactic physics, and on the other hand in CMB physics. And in particular, the idea is to have ground, balloon, or satellite experiment, which will have arrays of detectors of the order of 1,000 to 10,000. And in particular for the core plus satellite, or prism, or whatever they call it now, for which our group and your group here are working. So if we want to achieve this kind of project, we have to think in various things. The first thing is we have to increase the sensitivity. For that, we have to reduce the background noise. So the best for this is, of course, going to space, where the background noise is a factor of 10 to 20 beta directly. However, it's very difficult to have high resolution, because high resolution here we are thinking about telescopes from 15 to 30 meters. This is a bit too much for the space. The other thing we can do is to observe very long time. So this is especially good for ground-based experiments. But if you do just a fast calculation, given the sensitivity of Planck of current experiment, you have to integrate for centuries, roughly, to have the sensitivity we would like to have. So the only way we have is either to increase the number of detectors, having array of detectors, or to have much larger bandwidth. So both have been proposed. In particular, the large bandwidth observation has been proposed by the Pixie satellite, or anything in spectroscopy. And the other way would be to have compact arrays of detectors. In the compact array of detector part, there are currently a technology which has been well proved, which is bolometers, in particular TES bolometer, transition edge sensor bolometers. And the other one is the kinetic inductance detectors, which is the one I will discuss today here. And this, I think, is giving us the impression that this is an alternative thermometer technology that can be very good for very large array detectors and for instruments in millimeter wavelengths. So I just wanted to discuss the LZ effect, because a part of my talk will be discussing the result we have been obtaining in SZ. So as you know, a Sunyaev-Soloveic effect is just the inverse contour between CMB photons and hot gas in cluster of galaxies. And actually what happened is that if you look at the spectrum of the CMB as a function of frequency, we have a displacement of the spectrum which is relative and which is centered at 270 gigahertz. So you have a zero effect at 270 gigahertz. You have a negative distortion at frequency below and a positive distortion at frequency above. So this is an effect which is, I won't say easy to detect, but that has a very clear signature that we can try to detect with millimeter wavelengths, because it's roughly the main part of the spectrum to detect it is between 100 and 300 gigahertz. So the state of the art on SZ science is, of course, the Planck satellite. So as you know from people here, we have been working on Planck very hardly to have a first catalog of the Sunyaev-Soloveic effect, and in particular a catalog of cluster, and also a map of what we call the contour parameter map, which is a map of the SZ effect over the whole sky. And actually what we do in Planck is that observing at different frequencies, as is observed here, and so you can see that for frequencies below 270 gigahertz, for example 143 and 44, we have a negative effect, which is maximum around 140. At 270 gigahertz, we have zero effect mainly, and we go to frequencies above, we have a positive effect. So our proposition with NIKA will be to be between these two frequencies and maybe a bit more at high frequency as well, so that we can have a differential measurement of the SZ effect. So here you have the Planck map, with each red dot constitutes one of the clusters detected by Planck. We have something like 1,227 clusters in the catalog that have been mapped in 9 frequencies from 30 to 853 gigahertz. And what is probably the bad thing about Planck is that the resolution is not so good. So if we want to observe high redshift cluster, or with high redshift going from 0.2 above, we need to have higher resolution instruments. The other thing is that Planck cannot give us the redshift. So for that we need also follow-up observation with other optical instruments, for example. This is what is done here in the group at AEC. And for the other part, to have high resolution observations, we need large telescope, going from 15 to 30 meters, and we need arrays of detectors. So this is the main purpose of my talk today, how to achieve this kind of high sensitivity detectors with thousands of detectors. The redshift so far, we have a cluster which is roughly one redshift of 1.995 or something like that. So for that, we want to use kinetic inductance detectors. So this is a new type of detectors which have based in the superconducted LC resonators with a very high quality factor Q. This detector has to be cooled down to temperature of about 100 millikelvin. That has to be much smaller than the critical temperature of the material. In order to have a superconducting material, you need to cool down the material to a critical temperature, typically below 1 Kelvin or around 1 Kelvin. And to have this superconducting detector with high quality factors, you need to cool down then to much lower temperature. So I will show that. And at the end, what we have is just a resonator with a resonant peak. And when light arrives to the resonator, this is a picture of one of these KID detectors. When light arrives to the resonator, it's absorbed by the induction pack, and then this power is transmitted to the resonator. I will change the frequency of resonance. So I will come back to this just slowly. So imagine you have a dark detector. So we'll have a particular resonance with an amplitude given here and a phase. If we include power from the sky into it, so we will have a shift in the transmission and a shift in the frequency resonance because of the change in the kinetic inductance of the detector, and also because of the change in the resistance of the detector, we have also a change in amplitude. So at the end, what we have is a resonance which will change in frequency, in amplitude, and in phase. And what is really good for this kind of detector is that actually the change in frequency is directly proportional to the quantity of kinetic inductance change, which is directly proportional to the power emitted by the source. So we have really a linear detector here, which has power emitted by the source will be translated directly into resonant frequency. So the main thing is how can we actually, sorry about that, it doesn't go much further. How can we measure this shift in resonant frequency? So the first thing we have to do is to design kinetic detectors which are good enough to absorb millimetric wavelengths. So for this we have worked in two different designs which have been derived from what we call the liquid detectors. So these designs are here. So you have here one which is given for a single polarization one, which is composed by a fit line to which the detector is coupled. You have an inductance bar, which also is a kind of antenna on which you can absorb the light. And then you have a capacitor just to have the possibility of having a resonator. In this particular design, you can see that this acts also as a polarizer. So we can detect just one single polarization with it. And if you put those in different orientations in your focal planes, you can measure different polarization orientations. For intensity-only purpose, what we have designed is a two-polarization kit, actually, which is just based on the principle that we will have vertical and horizontal portions of the antenna, so that both polarizations are capped at the same time. And we have observed that the performance are very good, and so we have something like 90% of the total power which is absorbed with this kind of devices, to about 40 to 50% with the other kind of devices. So right now we are using those, and we are planning to use this for polarization sensitive experiments. So how it works? Actually, as I said before, you have to cool down a lot your detectors, and the reason is that if you look at here, you have here the resonant frequency for a kit, which is actually made of titanium, but most of the ones we have are made of aluminium. And you can see, with respect to the cooling power, you can see it from 200 milli-K to 820 or 80, the resonance shape we have. So you can see it for, if we don't cool down very much, we have a resonance shape which is not very good, a very low high quality factor. And when you cool down sufficiently, you start having resonant frequencies which are actually of high quality. So that is one of the reasons we really need to go to low temperature. And as you know probably from Planck, to go to low temperature, there are two main technologies: dilation cooling, which we are using, and adiabatic desegmentation, which is the second possibility. The second one uses magnetic fields, so it's a bit delicate for kids, but we are testing on it. But for the first one, it's perfectly okay to go down to 80 to 100 millikelvin. This is what we are doing right now. You can see that we cool down a bit less than that. We can even go to 140 and we still have kits that are good enough. So how do you do an array? So this is probably the good thing about kit, is that it's very simple to do an array. You just get a transmission line, a fit line, and you put several of those resonated coupled to the line, in the same line. So this is one of these days. So each of these is a resonator, which is coupled to the transmission line using a 50 ohm impedance. And you have an inductance, which is the kinetic one that will be modified by the light, and the one given by the substrate itself. And then you only have to put those one after the other, and you get an array. The good thing is that as you have an array here, you see that you only have one single transmission line. So this is by definition multiplexed. There is nothing to do more for achieving this. And this is what I show here. So this is the example of one of our all array of 129 kits. And what you can observe here is this is the frequency range, which is roughly about 1 gigahertz mean, or 1 to 2, and each of the resonance here. So you can see that in a single line we can have up to 1,000 kits. Of course, the problem is to be able to read all of them quickly enough. So this is the first thing. You can also see some observations here. Those observations were because we were using a spectral analyzer to give this picture. The spectral analyzer is not good enough. It's not really related to the kits themselves. So the other good thing about kits is relatively cheap to construct. So by contrast to bolometers that were mainly made in the States and somehow in some, kits can be done in Europe and actually we are leader in the kit manufacturing right now. And they are down actually in Grenoble, in the Grenoble labs, in particular at LPSC, at IRAM. Well, this is LPSC and Instituto. This is the CEA, the Commissaire pour l'Énergie Atomique, where we have a platform for a clean room and for the possibility of construct, and also at IRAM at IPAC. So within the same city, we can do the full process of constructing those arrays. And we also have a low temperature laboratory here, so we can have control of all the process, which is quite good with respect to previous tests we have done with bolometers. So now I'm going to try to discuss the case of the NIKA array. So NIKA is a prototype. Well, NIKA is actually an instrument for the 30-meter telescope at IRAM. And the idea here is to have an instrument who has a large number of detectors at two frequency bands, 140 gigahertz and 240. So this is a 1.2 millimeters and 2.06. This is a 240. This is a 140 gigahertz. And for which the scientific goals are multiple. As IRAM is a multipurpose telescope. In particular, people are interested in star-forming regions, characterization, solar system object physics, in particular Pluto, for example, galactic polarization study at high resolution, external galaxies, high resolution TSZ effect and KSZ effect, characterization of high redshift sources, in particular from the point of view of the SDD and the deep field number counts. And all this can be done from the IRAM telescope because of the resolution mainly, and the stability we have. So we are trying to get something like up to 5,000 detectors in total. So it will be something like 4,000 at 1 millimeter and 1,000 at 2 millimeters, from which the 1 millimeter will be polarized. We will have a field of view which will be 6 arc minutes roughly. This is the size of the beam of Planck at those frequencies. And what we want to achieve is something like 30 milliJasky square root of second per beam. This is what we call the specification. And we have a goal which is roughly a factor of 2 or 1 millimeter. And at 2 millimeter is 20 milliJasky and 10 of that. Just to give you an idea, for those interested in that effect, that will correspond to something like 2 to the power 10 to minus 5 per hour for observing in one single beam. So if you put this into a Planck beam, you have to reduce by a factor of a square root of, from the top of my head, but something like 200 roughly, because we have something like 12 arcseconds and 17 arcsecond beams. So the status of the project is that has been approved, is now funded by the CNRS INR grants. We have started the construction of the cryostat, and should be commissioned by the mid-2015, and should be ready for use beginning 2016. So in order to get there, what we have done is to produce the first prototype of the NIKA2 camera, which we just call NIKA. And this is just a reduced version of it. Same frequencies, same beam pattern roughly. This is actually the measure 1, 12.5, 11.5, and with a reduced number of detectors. Actually, this is very old transparency. Now we have something like 200 and 150 here. And we have, of course, we have to reduce the field of view, so we have something like 2 arc-minute field of view. And we have already achieved, since last campaign, 25 milliJasky square root of second per beam and 10 milliJasky square root of second per beam for 2 millimeters. So this is already in the specification, and for the 2 millimeter, we are nearly in the goal. But of course, you have to keep in mind this is only 200 detectors. So now we have to scale them to 1,000 and 4,000. But in principle, we are doing well. And for the control parameter, that was last campaign was 3. I think we are now more like 2.5. So we have also improved here a bit. So the NIKA prototype has had many campaigns. The last one was in February 2014. And we have a cryostat cooled down to 100 milli-K. We have a dedicated optics, simultaneous dual band observations. And we have a dedicated readout. And we are now able to do both 6-axis scan or raster scan for other astronomers and LISA US scans. So I'm just going to go very quickly about this. If you have questions, please just stop me. because the time is limited. So this is actually the cryostat here in the IRAM 30-meter telescope. This is the dilution bank pumping. This is our readout electronic system. You have here the input window of the cryostat, which you can see is very small. With this is polystyrene, and we have a lens here to first order. And you can see that this is a relatively small instrument that can be controlled by just one person, well, two in practice, with simple two computers. So what I wanted to show here is that we do everything ourselves. So this is probably why we are so happy with it. So for each of the detectors, we have an array, a KID array detector, which have, this is 200 now, 200 pixels for the 1 millimeter and 150 for the 2 millimeters. And the principle is the same. So you can see here a plot given the resonance for the current arrays. So you can see this is pretty good, it is pretty flat. And each of those is 1 pixel. Just to tell you, this is a fit line going like this here. And then it goes out, well, it starts from here and gets out here. And each of these square here is a pixel. So for the dedicated optics, of course, as is a particular camera, we have to have a dedicated optics for the IRAM 30-meter telescope. I think the most important thing is that even if we have complicated optics with several mirrors to get the light from the 30 meters down to the camera, at the end we are using a simple lens optics to get the light to the array. So there is not necessarily any particular system to focalize into an array of this type. So this is not just a standard optical system. And the only thing we have done is a splitter here that allowed us to have observation of 2 frequencies at the same time. However, from the point of view of electronics, this is a bit more complicated, because as I said before, we can multiplex those detectors. So we are having now a multiplication factor of 400 to 500. And for this, we have developed a full new electronics that has the following principle. In practice, what we have is, in the transmission lines, you will have kind of a filtering of the input signal at the end. It's like you have a filter which have this resonance in it. So to measure those resonance, the best is to input a signal and check how it has been filtered through the telescope and through the cryostat. So for that, what we do is just input a series of sinus and cosinus, the Fourier series. It goes through our detectors, and then it gets out. We compare it what we had at the beginning, and then we can deduce what is the shift in frequency. And so we can do that going from a bandwidth about 500 megahertz. So that's why we can, as KIDs are separated by roughly 1 megahertz or 1.5 megahertz, we are able to sample up to 400 or up to 500 in base cases. So I won't get into details, just please ask questions if you need it. So how it works. So once you have the electronics, now you have to convert what you measure into shift in frequency. This is likely, it's not as simple as I might think at the beginning, because we can now sample completely all the frequencies. So what we do is we sample specific tones, which are centered in the main resonant frequency when the KIDs are dark, and then seeing how the change in the transfer function of the system has been, we can reconstruct the shift in frequency. So this is what is displayed here in this circle. So you can see here, this is the IQ plant. So this is the imaginary power for I, real power for I, and imaginary power for Q. So each resonator in the IQ plane is a circle. So you get a first measurement of I and Q at a given frequency, and you can also just, by changing the slightly frequency, you can get a measurement of the derivatives over the circle here. So this is what represents here. You measure IQ and the derivative. So you get displaced because now you put a source in your detector, and then you can measure the displacement of the IQ within the circle. And then what you can do is just, by measuring the IQ and the derivative here, and as you know exactly how the derivative transforms into frequency shift, because you have used 2 tones for this, then you can directly measure the frequency shift. Oh, sorry, this is not the right one. I think you can directly measure the frequency shift you have. But this is a complicated formula, but what is important here is that at the end, the frequency shift you measure is proportional to the power incoming from the sky. So you have really a proportionality, which is very good. This is what I wanted to show here. So this is actually the shift in frequency as a function of temperature of the background. So we have done this in the lab. And though we have go from temperature down to 20 to 30 Kelvin up to 300 Kelvin, and you can see that the detectors are completely linear using this technique. So we observe no departure of linearity within those range. However, I have to say, because it's still a problem here, is that this is the shift in frequency. However, to measure this shift in frequency, you can imagine that if you put too much power, the resonance will just shift completely from where you were measuring. And then your transmission will be 1. So in order to be able to measure, you have to re-shift your tone of reference so that you can follow the resonance going on. And this is what we have developed. And using this technique, then you have a real linear detector. So the thing is that this is actually very useful, because when you are observing a millimeter wavelength, you are dominated by the atmosphere most of the time, and then you would like to have monitoring of the atmosphere. And actually, this linearity is really strict. You can measure the opacity of the atmosphere directly. So this is what is brought here. So you have a sky opacity as a function of the campaign. This is for the 4th and 5th campaign. We were, sorry, 5th and 6th. And what you have here is the 2 millimeter opacity in, yes, 2 millimeter in red. 2 millimeter in blue and 1 millimeter in red. And in here in green, you have the measurement from the meter at IRAM. So for those who have observed at IRAM, you can see that this is the NIKA camera. We are able to measure and monitor directly the atmospheric emission. So this is very good because it will be used in the data analysis I will show afterwards. So we have, in real time, we do a correction of the atmospheric absorption. So now I just wanted to show this plot because we started working on this something like in 2010, at the end of 2009. And then we have been trying to improve in sensitivity. And actually, the progress was quite fast at 2 millimeters. You can see that after a few years, the main progress was here that we were using a low-noise electronic, the one we have developed, specific, in 2011. And then you can see that we reached the specification very quickly after 2 years, and that right now we are right at the goals. 1 millimeter was much more complex, and the reason for this is that these sensors are very sensitive to the power of the low-noise amplifier. So we have to be careful to have very good low-noise amplifier in the cryostat. And until then, we were having problems in tuning the power of the amplifier and the kits. So that was the main reason why we were doing very bad until very recently. But for the last 2 campaigns, we have optimized the point of working of the detectors. And we are now, right now, at the specification and below. Well, this is, of course, preliminary. We are reanalyzing the data, but for the last campaign, I think we are right now at the specification. So this is improving quite a lot. So just to give you a flavor of this work, as I said, we started in 2009 having the first light with kits. We have done up to now 8 campaigns. From 2011, we had already the 2 millimeter camera that was working pretty good. And now from 2014, for the January and February campaigns, the 1 millimeter camera is I would say, to a state-of-the-art experiment, a bit better than, well, it's a factor or 2 better than Mambo 2, if I'm not mistaken. And what we had on February, and that's why I'm here, is we had the first open scientific run with something like 20 proposals, from which I think the 15 has been mainly completely observed. So this is working well. Finally, even if the weather was not very good, the kids were able to cope with it so far. So hopefully the observer will be happy on bad weather conditions. But okay. So what is the status of NIKA2? So this is NIKA that I explained. For NIKA2, we have designed the cryostat. So you can see here. This is very, very large cryostat. It's something like 2.3 meters in total. It has a nose here where the main mirror will be. And all this part here, you can see here, it will be cooled down to 100 mK. So this is something like 50 centimeter or 60 centimeter box that will be put down on NIKA. We are already constructing 1,000 and 2,000 pixels array. So this is the first one that we have. We have tested them, and well, we cannot test more than 100 pixels at a time. But for those tests, we are at the sensitivity is expected. And the cluster just arrived 2 weeks ago with the pulse tube elements, which are right now here. And you can see the pumping bank is in these boxes here. So that's for the group here. So you can see something like a box like that. For 2 pulse tubes, something for 1 pulse tube, it should be roughly half of it. So this is work in progress, and I think will be ready pretty soon, at least from the point of view of the detector. So you have a picture here, so you can see that the size of those devices is only 80 millimeters across. So they are not that large. It's something like that you have 2,000 pixels at 1 millimeter and 1,000 at 2 millimeters. I think the main problem here, well, you can see, this is a very nice picture. The main problem here is that we have to do some kind of bonding from the pixel to the line, fit line. So far we are doing this by hand, as many people. So for those detectors, it's taking a long time to get ready to high quality, but we are able to produce those. So you can see here, this is the input and output for the 4 fit lines that are implemented in this one. So I'm going to go just a bit about that analysis, because I know some of the people here are using the 30-meter IRAM telescope. So just to explain you what we do, and in principle just to get some feedback if necessary. So far we are working using what we have been using for previous runs. So it's very simple analysis, I think. It's just we are using our own file system, raw data. We are using the reconstruction of the focal plane directly using our data. We do the calibration on planets, and we check on planning calibrators from the IRAM. The opacity correction is using the sky dips I presented before. In practice, yeah, we can just measure the absorption of the atmospheric emission and then correct directly. We use the Kinetic because cosmic rays for any other detector millimeter wave are a problem. So there are not many cosmic rays on the ground, but there is still some that we have to cope with. We use a common mode correlation so far to avoid atmospheric emission. And we have to filter fused tube rays, which are very high frequency, so this is not very a problem for us. And we are projecting into maps. So you have here a few pictures. I will go through it right now. So the first thing is grid removal. So you can have here, this is a typical timeline as a function of time. So this is flux in JavaScript that has been already calibrated. You can see here how they react. You can see that it's pretty good. And you have some spikes here which come from cosmic rays. By contrast to bolometer, KIDs are very fast. So the time constants are below 1 millisecond compared to bolometers, which are 5 to 6 milliseconds for Planck bolometers and more like 10 milliseconds for TES. So this is an improvement. And you can see this is just a single point because we are having frequencies of sampling which are of the order of 35 to 40 Hz. So this is just a single point in our data. So this is easy to remove. I think I forgot a couple of it. Okay. Yeah. Sorry about that. I just have to come back. Okay. So we are using a single mode correlation. Where the thing is just we construct a template of the atmosphere, the first template. We subtract it from the data, and when you subtract, we of course remove a bit of the point source. For example, you have here. This is the case of a planet, I think, and then you remove a bit of the source. That gives you a slight offset in the measurement. So what we do is just do a map, flag the source in the timelines, reconstruct the common mode template of the atmosphere, and then reconstruct a map, and we do this interactively so that at the end we are able to measure the source. In particular, this works very well for point sources, and we are able to apply this to extend these sources up to, I would say, well, being optimistic, up to 5 to 6 arc minutes so far, given that the field of view is 2 arc minutes. So this is the first thing. So we measured the beam, and we were relatively happy about this because if you think about detectors that have no homes, you can imagine that the beam is very, very complicated to first order. So you have here the picture for the beam for the 1 millimeter, 2 millimeters. So this is power as a function of distance from the center of the source. This was done with the Planck. And you can see this is 1 here, and this is decreasing as expected, and the blue lines. And you have here the total power, the integrated total power. So you can see that relatively to up to 100 minutes, we have roughly 99% of the total power. So this is quite encouraging. So we have a beam pattern which is relatively well understood. It's not Gaussian, so the Gaussian part will be here. So if you have a horn, you will have something that will decrease here very quickly, and you will have some wiggles. And this extra power here may come on the one hand from crosstalk, which is pretty small, but is on the other 1/1000. And the second part is because of the fact that we don't have a horn to reduce close nearby side lobes, I would say, if you can say. You can see also that if we go a bit further, you can also see actually the telescope structure. So this is the diffraction pattern of the IRAM 30-meter telescope measured by NIKA. And you can also see the arms, which are particularly very well visible at 2 millimeters. So I think we have sensitive measurement and precise measurement of our beam. I don't have the picture here, but a very large distance, we have a beam pattern which is compatible with the one measured by the IRAM using Holmes bolometers. So this is okay. So we can reconstruct the focal plane. So you can see here, this is the focal plane of 1 and 2 millimeters. You can see here that we have a relatively good coverage of the focal plane, which is quite homogeneous, with pixels all around the focal plane. So this has been slightly improved for the latest campaign, and we have increased the number of pixels in the center, and slightly decreased the number of pixels in the outside. So but we have a coverage which roughly gives you 3 detectors or 3.5 detectors per beam. So this allows us to reduce to increase the sensitivity. So this is how we actually compute the opacity. So what you have here is the frequency shift as a function of air mass, and you can see that this gives you the typical opacity curve we are used to. So you expect here to have an exponential curve of shift of frequency or power with opacity. And then we are able to measure the mean opacity, and from that we can correct the data. So what you have here is just the data of Uranus after correction from opacity, and you can see the dispersion is very small. It's about 10%. And this is what we have been computing. We will expect for our systematic errors at the time. So I just wanted to show you that NIKA is good for doing SZ. So if you remember, the SZ emission was a differential in frequency. So in particular was negative at 143 GHz, and nearly now at 243 GHz. So you can see we are actually, if you look at the transmission of the NIKA as a function of frequency, you can see that we have really a peak at 140 and another peak at 240 GHz. You can also see here the bands from the atmosphere. So you have ones which are for water vapor, and then other ones which are given by, you cannot see because they are the dot lines here, which are given by oxygen. So right now we are well centered in the band. We are able to change the bandwidth just playing with the characteristic of the detectors. And we have optimized the 1 millimeter band to cover as much as possible. So this is a factor of 2 beta that we used to have for the previous ones. So as we have 2 bands, we also can monitor the atmosphere with the high frequency band, for which we have no Sunyaev-Solovich effect, and then subtract it for the low frequency one. I won't go into the details, but at the end what happens is, I'm sorry, I will go. What you have here is clearly the atmospheric emission in the raw data, and then you just subtract a template for the 2 millimeter, for the 1 millimeter band. At the 1 millimeter band, you get something which is very flat. So you can see we have a good monitor of the atmospheric emission using the high frequency band as well. So this is what actually we do for the Sunyaev-Solovich emission. So I just wanted to present you a few results from NIKA. Of course, it's not exhaustive, so I just have chosen a few of them to give you a flavor of the kind of things we can do in science with those. So in particular, this is a very nice object that we observed very long ago. This is a FLS-3 that we observed at 2 millimeters. And what you can see here is a map of nearly a point source. It's a high redshift galaxy of about redshift 6.5, and this was one of our first map at high redshift. For this particular map, we obtained something like 13.6 millijoules per root of second per bin. It was actually quite good in just a few minutes of observations. We have re-observed that, and we have a comparable map just in 50 minutes. So we have been proven that our factor of 2 is real in the data. So we are able also to observe extended emission. So this is, for example, a map of the Horsehead Nebula, where we have weak and extended emissions. So you have the map here at 1.25 millimeters, 2 millimeters, and here you have the spectral index just computed from the ratio between the two. And just for comparison, you have here what was done by Mambo at 1.2 millimeters. So you can see that the 1.2 millimeters is already at the state-of-art emission, and I think this is the first 2 millimeter map I know, at least, or the Horsehead Nebula, or maybe another one. And then just to give you a flavor, if you look at here, you have here the integration time and the noise, and you can see that it's very homogeneous over the whole period of observation. So we are being able to get a good number of detectors which are good enough to observe, and this is reportable during the time of observation, typically 10 to 20 minutes for this particular source. So we have also observed a cluster of galaxies. So this is RHG 1347.5 minus 1145. This is a well-known cluster of galaxies because it's the most, well, one of the most brilliant and probably the most brilliant cluster in the sky at those resolutions, of course. And we have produced a 144 GHz map. You can see here, this is the cluster of galaxies that show up like a decrement in flux. So this is a direct measurement of the Odysseus effect, and we have been using the dual band common decoration technique, and we are able to recover large angular scale that you can see here. So this is something like 4 minutes across. And the integration time was something like 5 hours, from which we have something like, I will say, 20% calibration time as well. So this is the first, I think it's the first SZ observation made by the KID instrument. So now you can, actually we can do a lot of physics with this cluster because it is a quite particular one. So just to give a flavor, we can compare it with the X-ray data. The idea way to compare to X-ray is that the X-rays are mainly sensitive to the density of electron square, so where we have a lot of density of electron, and the SZ is more sensitive to the density but also to the temperature. So there is a relative effect that allows us to measure with SZ emission there where we have shocks, where we have relatively low density but high temperature. So this is what's happening here. So you have, of course, the NIKA map here in blue, and the red contours are the one from X-ray. You can see that there is an offset between the center from SZ and X-ray, and that there is an excess of emission in the south part of the cluster. And this is because actually this is a merger cluster, which you have a center cluster which is quite stable, and there is another cluster which is just passing through like that. And we are right now observing the shock of the two clusters. So, and this is a test try to show this. So if you look at our data, so this is our data here. We do the simple model using a pressure profile, so you can measure what will be the emission from the first cluster, just concentrating in the top part of the map. And then when you subtract that, you can see here clearly the excess of emission coming from the shock. So this is not the first time, of course, that this has been measured, but this is probably the, I will say, the more detailed or the more resolved image of this effect so far. And then with this, what you can do is a bit of physics. This is what we want to do for Planck. So if we want to do a follow-up for Planck, is because once we have resolved cluster, we can measure very precisely the pressure profile. So if you come here, you can see that the intensity shift, or I would say intensity differences, is directly proportional to this function, which is the differential spectrum function I said before, the fact that we have negative below 217 and positive above. And this pressure function, which is just the integral of the pressure across the line of sight. So if we have a resolved cluster, we are able to measure this integral here, and then we can measure the parameters actually of the profile of the cluster. And in particular, those profiles will be related somehow to the dark matter content of the cluster and also to the baryon content of the cluster. So in some sense, we are able to resolve the dark matter profile and baryon matter profile of the cluster with this technique. So this is what the result we have obtained. And in particular, we can measure the total power and the Kerr radius. And this Planck cannot do. And this is the main reason to have a follow-up with Planck, of Planck cluster, is to be able to measure the Kerr radius of the clusters that give information about the physics. So the other thing we can measure, this is just data from the last round. So this is very preliminary. I just show you to give you a flavor. This is another cluster we have observed. This is MAX G077537. This is a cluster which is a redshift of 0.55. And actually it's a complex cluster because there are at least 4 substructures. There is one cluster here, another one here, and 2 here. I don't know if you remember this. And actually what we observed is that these clusters are moving with respect to each other differently. So in principle, we should be able to observe both the Sermon-Sunier-Soloviev effect and the KSZ, which is proportional to the relative difference of the cluster with respect to the CMB. So in this particular thing, what we would like to measure is to measure the SZ effect at 2 millimeters, we expect it to be negative. Measure it at 1 millimeter, where we expect it to be positive. And then, in principle, the quality of the data is not good enough. So you can see here that we have an excess of positive signal here, but not here. And this could be explained, in principle, by the KSZ emission. That will be different between the clusters in this position and in this position here. So so far it's very preliminary, so don't take this as a measurement of the KSZ at all, but just to show you the power of these kind of observations. And finally, I just wanted to finish with, this is more to thank our colleagues at IRAM, in particular Israel Hermelo, who has been helping a lot us for producing those observations. And this is one of the sources he wanted to observe. So this is a dwarf galaxy, GC 1569. And here you have the first 1 millimeter map of this source at here and here. And here you have the spire maps we had before. So you can see that we are able to recover very fine structures with the current data we have. So I just wanted to finish by the fast conclusion. So I think the technology of KID is now ready to be used. We have proved this with the latest observations. A promising technique, an alternative to bolometers, in particular in some particular regimes where we want to have many detectors and we want to do them by chip. It can be extended in principle to 70 gigahertz. I didn't show that, but it could be possible, just changing the type of material we use for fabricating the kits. Can achieve very accurate calibration, up to 10% already, and we are hoping to improve that, knowing that absolute calibration on the ground cannot be better than 5%, which is given by the calibration of planet by Planck. So this 10% is just a factor of 2 with respect to the best absolute calibration you could expect, or the optimal absolute calibration. The NIKA2 campaign the NIKA campaign has been a success, I think, and we have excellent data. And the NIKA2 is in good path, should be, I think, ready for commissioning in mid-2015, and hopefully ready for observation in 2016. I think the other thing, this is probably why I came here, is that KID could be good also to observe CMB emission. This is, of course, working project, but we are very keen of working with the people here at AAC for making this a reality. So I will stop here.
Okay, thank you very much for Doc. So now time for questions.
I have a couple of questions. One is related to the sample case that you had in slide 52.
Sorry,
slide 52, 2 slides before.
Slide 52?
The one,
okay, this one.
Commenting on on the kinetic effect. So just for curiosity, what is the? I mean, it is that internal motions inside the cluster, because I cannot compare that easily from to microgravity. What is the velocities? What are the velocities?
They are pretty small. I don't have from the top of my head, but this is pretty small. It's just differential velocities of clusters in the same supercluster. So it's small. It's
about how much? I mean,
it's about 100 something. 100 I think or two. Oh. It's very small. The effect is very small. That's why we think. Well, there is a paper has been out by Mustan that try to measure this for the first time. And what they do is they model all the components of the clusters, and they do just from the modeling and having 1.5 frequencies try to see a difference between the two maps here. So it's very small, and they have something like 2.5 sigma detection with a model dependent. So it's pretty small. This is just to show this is a possibility. We have something like 10 hours of observation here. To be honest, if you get the difference as it is, we are still a factor of 2 down away from having a detection of the case if the model is correct.
Okay. And the second quick question on the calibration. So the 10% is just because of the atmosphere, right? Is essentially.
The 10%, yeah. Actually, the 10% you're observing here is actually the funny effect is that when the atmosphere changes a lot, the beam pattern of the IRAM changes as well, sufficiently to be observed. And then, unfortunately for that one there, we have very bad conditions, weather conditions. So we have opacities from 0 or minus 0.1 for a 2 meter up to 0.4, 0.5. So this is taking all into account. You have 10%, from which I think 2% is just due to this difference of the beam pattern directly we have not corrected for. So we are hoping to get better than 10% once you have corrected for opacity and you have also correct for the different beam pattern. Because for calibrating, what we do is very simple. We just assume that we have point sources in the field, particularly for the planet. We just fit a Gaussian to it. And from this, we deduce what we call a point source calibration. And then if you have another point source, you can just apply this calibration to the other point source directly, assuming the same full width and maximum for the Gaussian. If the weather is different, so the beam pattern will change, will get broader, and then your fit will be worse, and this is what is dominating the error here so far. So I think we can improve on that.
I'm quite happy that you are here because I'm one of those users of the NIKA. And
yeah, I know.
So I have a lot of questions for you. How long are you staying?
Today.
Just today, okay. Okay, I'll try to talk to you later. Yeah. One of the questions is about the positions, the coordinates. How good are the coordinates?
I would say that we are claiming pointing errors of about 2 arcseconds. We know, in principle, you can do much better with much better. You can do down to 1 arcsecond with the IRAM telescope. There are 2 main problems, to be honest. This is really a prototype, so it's not really well adapted to the IRAM system so far. So what we are doing is we are using, it's a bit technical, but you are an observer, you might know. We're using what they call the NIKA, the Elvin server, which allows you to give to have the pointing on real time. So we get this pointing in real time. We include it in our data directly, so that this allows us to produce map very quickly, just in 1 minute after the observations. And then what we do is just to check this pointing with the reconstructive pointing used by the IRAM itself, what they call the IMB-fit antenna files. So right now we are observing that we are not taking into account what they call the track errors, which sometimes can be important, and this is limiting our. This is our main limit in the pointing error. But I think 2 arcseconds is still reasonable given the data we have.
And the plans for the next couple of years is that NIKA will be offered for
NIKA
4 semesters, and the NIKA2 comes?
Yeah, normally NIKA2 should be installed mid-2015. So normally we should have 3 more runs of NIKA. So the first one should take place on June this year. May, June, and well, the proposal has to be set before the 13th of this month. So this is quite fast. And then we will have a winter time more, and we are hoping to have an intermediate one, something like in I will say October for polarization purpose. That will probably not be open, but we are open to collaboration if some people have some idea of sources that we could observe. And then we are hoping to have a last one, something like just after the January campaign, the winter campaign, or February campaign, in the spring somehow. But this is still under negotiation. And after that, we will be probably stopped for half a year if everything goes well. And the first NIKA2 campaign should be on January or February of 2016.
Thank you.
Okay, more questions? Well, if not, I have also one question myself, and is, can you tell us more or less what is the range of wavelength or frequency that this detector is applicable?
Okay, well, actually, I have a transparency somehow if I manage to put it. Is this one here. So you can see here in this plot, this is what we are able to do right now. So depending on the material, you have niobium silicium in red, titanium in blue, and aluminium in green. So aluminium is what we are using right now, which is the most, I would say, the easier technique and most standard. And then you can see with aluminium, we are actually limited by the critical temperature, which is about 1.3 Kelvin. And then we have a cutoff, a strong cutoff, about just before 1 gigahertz. So we can do nothing to get down there. If you use titanium, in this case, the cutoff is much farther down. We can go down to 50 gigahertz. But I will say the transmission is not proved to be good enough yet. So you can see that this is a hint that we can get down, but the transmission should only point to. To get a better transmission, we have to adapt what we call the backshock, which is roughly the size of the substrate on which the other material is. This might take some time. I'm not sure that titanium will be the best technology, but because it's a very expensive and complicated to get material. However, the niobium silicium is probably our best option, because depending on the mix between niobium and silicium, you can get to very low temperature. So we have already obtained something like 1 Kelvin. And you can see that for this material here, we have a better transmission around 100 gigahertz. So we are positive, unless we have not demonstrated yet that we could get down to 70 gigahertz using the niobium silicium. And the good thing is that we have also enhanced in Grenoble a group in our lab that is able to produce those substrates. So I think this is probably much more easier for us to keep going on niobium silicium than going to titanium. But if it doesn't work, titanium is definitely possible.
Okay, thank you. So, more questions? So if there are no more questions, so let's thank again our speaker.
Thank you.